then you can spend over the weekend. I sometimes came on Saturday, sometimes Sunday afternoon, and I usually go into the students' the room. Then sometimes nobody there. Sometimes one or two are there. But weekend, I really feel you should really spend the time for something else. I feel personally at least a day. Some of you may not want to spend the whole day away from books. It's all up to you. At least I feel, to my lab, I encourage students to spend something else at least a day over the weekend, maybe half a day, whatever necessary to change your thinking to something else. So anyway, spend a couple of hours as a measure, maybe an hour, maybe too short, maybe 2 to 3 hours to really set it up, the MATLAB code or so, whatever the code, then plot it, then get the feel of it, then move on. So that's what the whole reason to assign to generate the shock spectra. And I gave again, input excitation is a triangular pulse. Then you will learn today the examples, get the feel. Then when you do the over the weekend the mini project, then you will feel the similar things. Okay, and this is as I explained yesterday, the day before yesterday. This is real data. So this is one of the velocity measured by the velocity meter at the very sturdy, very rigid locations. So that's what, and this is right at the bulkhead, very stiff area. Why you use a very stiff area? Why you mount a velocity meter in the very stiff area is to really, your interest is to measure the gross dynamic response. You have no interest, I don't have any interest to measure the local, the response, gross response, okay? So that's the reason, and that's what the velocity meter is mounted right on the bulkhead, okay? And this is kind of a wave form. So starting from like a 16 millisecond up to 16 millisecond, it was very quiet. What would be the reason? What would be the reason? Well, shock may take such a 16 millisecond to get to the location where the velocity meter is, okay, whatever. So then bang right here, then it really goes up. This is a z dot, okay? So expressed as a feet per second. Feet per second. So in this case, peak value is about about 10 feet per second, which is about divided by 3.2. It's about 3 meters per second. So that's a very good expected value. This is SSTV. Is not this is not, SSTV is submarine shock test vehicle. As I mentioned the other day, it is like a diameter is the same as the submarine diameter, and the segment is some portion of the submarine. It's all unclassified the SSTV configuration is concerned, and it's all information is in mil-spec 901D. So it's all, you can find the dimensions and everything in internet. If you punch SSTV, it should show up, okay? But not surface, not FSP, floating shock platform. But anyway, regardless, this is one of the measurements which makes sense, okay? And all this zigzag is like high frequency, as I mentioned the other day. And what would be the rough high frequency range? So, for example, if you pick out the 1 little segment, or you can blow it, then you can measure the 1 cycle in there. Manually, you can do that, roughly to see what frequency of noise level of signal you're dealing with. Of course, you can throw into frequency domain, then you can really see all that too, okay? So, but don't say that in the field, I'm sorry, I don't have a notebook, so I can't do it. That's wrong answer. Then you are out. Okay, I think I mentioned to you in the oral doctoral qualifying exam, all the examiner was sitting here, about half a dozen, about 6 examiners are here, raised the questions. Then the student said, I'm sorry, I can't do it because I don't have a MATLAB. That's the wrong answer. So you have to have as engineer, very good intuition, I demand it, and understanding. Then you can do it. In the field, as the preliminary answer, you don't have to get exact answer in the field, but I demand you should, once you have logics and feel, then you should immediately say or comment about it, okay? So you can tell. So if I approximate this base excitation, this is base excitation because it's bang onto it. We don't have any data on what size of the charge to generate this, or what's the standoff distance. We don't have any data. This is only data, right? So it's a base excitation. So you can apply this to get the shock spectra. You can apply this to the base of the shipboard equipments, right? To the undamped single degree of freedom system, right? By a particular shock loading, this is what the particular shock loading is, right? Then you can get the shock spectra, right? So if I give you all the digitized value, right? If I give you the digitized value, then you can just get the shock spectra. You can set it up all that. That's what like a weekend mini project is. And we are going to use this signatures to get to feel. If I approximate this as a straight line up to here, then coming down, acceleration and deceleration between like a 15 to 40, and this is something like over here, which is 16, maybe 20, roughly, right? So then you can use exactly same the equation set, right? Then when you approximate this as a triangular pulse, as I mentioned the other day, the high frequency component, high frequency area is really down. Why? Because all this high frequency noise, this is a high frequency noise, all the zigzag, that's gone. If you approximate that, you have to have a full understanding. The question is, what is your interested frequency range? Is it lower frequency range? Is it upper frequency range? That you have to know. Or you can tell, when you throw this in the shock spectra, you would know where the peak is. Then you can tell what the range for spectra is. Then for the particular shipboard equipments, you should have like a vendor's the spec. Then vendor's spec give you the shock spectra, design shock spectra, that this particular the equipment can survive, vice versa. Okay. And this is base excitation, and then, as I mentioned, then you apply. This is as I shown here, response of 100 Hertz single DOF system to recorded motion 40 millisecond from 0 to 40 millisecond, but first 16 millisecond was quiet, right? Then you can really start from 16 millisecond. There are a lot of different ways. You can start, reset to 16 millisecond as a 0, then move on, right? Vice versa. And shown in this, we saw it as a base motion. So response of 100 Hertz, I just pick as example 100 Hertz single degree of freedom system. What does it mean? So that means 100 Hertz, right? So you have a basic equation, y double dot is a function of time t, of course, is omega n square, and yt is equal to minus z double dot, base excitation. Then omega n is, of course, radian per second. So if you convert into the Hertz, 2 pi fn square. So 4 pi square fn square, this portion. So then 100 Hertz for that particular one, you replace Fn by 100. This is 100 squared then, okay? Then you can solve the problem. For this case, you can solve in closed form solution, then apply, because the input excitation, base excitation you could digitize it and input that, or if this is a triangular pulse, you have the closed form solution. Then you can plot this. Then as you see here at 100 Hertz, this is 100 Hertz case, but you should have like a 1 Hertz, 2 Hertz, 3 Hertz. You can just do the do loop and then pick out each omega n. You have to pick out the maximum absolute. Negative, positive, doesn't matter. Okay. So in this case, this happened to be the max. So then this is 0.19. Then in the frequency domain plot, which is a shock spectra, you plot 100 Hertz here. Then plot 0.19. This is SY, relative displacement spectra. Of course, a shock spectra. Then you can plot 1 point. Then you have to go through like all different frequencies. Then this is a rough plot. You can do this kind of the plot much nicer, but in this case is a plot in log. This is 10 to 100 hertz, and from 100 hertz to 1000 hertz. It's log scale. This is also log scale. So log scale plot is very popular for shock spectra, and really most of the shipboard equipment, whether it's a surface ship or submarine, for shipboard equipment response usually is below 100 hertz. Above 100 hertz usually don't go there. Well, depend on the equipment. The equipment tell you where the major frequency contribution for that equipment is. So usually below. So for that, just the previous page, for that SSTV base excitation, as y is concerned, the pseudo velocity sy dot is something like this. Okay, so here is a y dot, and it said the pseudo velocity, pseudo shock spectra value. So here it just indicate as a pseudo velocity. What does it? Why he put the pseudo here? I mentioned the other day, you know, pseudo maximum could occur after the application of the shock. That's what it is, right? Pseudo. Y double dot, y dot is equal to the x dot minus z dot. So when you, if anything, say pseudo spectra, z dot assume the action of the z set to 0. Okay, that's what that means. It's a very good approximation for shock. Application of the shock so fast. Okay, that's the reason. So this is like a shock spectra value plot based on that actual measured the base excitation. But then I want you to compare, and this case is approximate that actual measured data by triangular pulse, then apply on the base of the single undamped single DOF system. If you approximate this like this, what the shock spectra shape would look like? What do you expect? What frequencies are gone? High frequencies are gone, right? Right? Yeah. High frequencies are gone. By looking at this, I'm not going to just rotate, but like this is with the high frequency, so somewhere around here, this is a high frequency side, this could be gone, right? But that means this is really way down. So let's look at it. So this is the curve. This is the one for straight line approximation, and the high frequency level is gone. That's what you expect. So once you get the feel, then you can tell, by approximate this, high frequency would be gone. So shock spectra, there is no such a thing as universal shock spectra. The shock spectra is totally based on your input excitation by particular shock loading. One of the mistakes people does in reality is based on their result, and they feel beautiful result, and treat that as universal shock spectra. That's absolutely wrong, because it ties always with the given input excitation. So this area is a Z. This is 100, this is 10. So as you look at this, it used to be going like this, but this is all going down. For what case this would be okay? Your major frequencies is way below the 100 Hertz. This is perfectly fine. Perfectly fine to use a triangular pulse, because above 100 Hertz, my equipment doesn't respond because it's way away from the resonance. Okay. So now the same signature, 16 to 40 Hertz. So rather than triangular pulse, I want to just make it, it said hand average approximation, just to you by just throwing the line, and just to go around it here. It's not straight line, it's curved line to approximate this input, the velocity data. Then if I just use this hand averaged data as input, the shock spectra is concerned. Can you feel the shape? Yes, because still lots of high frequencies are gone. Above 100 Hertz are gone. But below the 100 Hertz, this is a lower frequency, so they're still there. And as you see the next page here, pretty close to, this is pretty close to the shock spectra response, shock spectra based on the original measured data. But still, we lose a little bit high frequency, it's not bad. Who controlled all this? You control. Okay? You control. And this one is so rather than up to 40-second data, I extended it to 70 millisecond data. So from up to 40, I extended. Then as extended, noise is not there, because bang, then it has a high frequency response. It's a transient area, but after that, it really kind of the vibration mode. Okay, so high frequencies are gone, but low frequency components are there. So rather than using up to 40 millisecond, how about using up to the 70 millisecond? Well, then you can do that. You can apply the signatures as measured. Then you can feel it from the shock spectra based on up to 40 millisecond. Now if you add this up to 30 milliseconds more, then what do you expect? Can you visualize what area the shock spectra are going to be changing? Of course, because this component, low frequency components, are more in the shock spectra. So below the 100 Hertz, your amplitude, shock spectra amplitude would be higher. And this area is all included, it could be there. And okay, if I approximate that as a triangular, just straight line segment, triangular, straight, like a straight line approximation, then what do you expect? High frequency components in like above 100 Hertz would be down. But the still low frequency range would be higher. So that's pretty good. So who decide to make the shock spectra? You decide. So up to 70 milliseconds. 70 milliseconds, you think it's much longer time? It's 70 over 1,000 seconds. 0.07 second. Extremely fast. This period is longer than 70 milliseconds. So that's what you have to have a feel, okay? And we'll see. So this is the 70 millisecond as is. So in low frequency, this is the region frequency. This is around, here's a 20, about 25, 27 Hertz area is high. So 27 Hertz, this is due to this area. You can think of this area, this, look at this, make it one long, the segment, that's roughly, you can tell from spectra, roughly 27 around that Hertz. And this is as is, as you see, this portion is up due to 40 to 70 millisecond contribution. High frequency is down because you eliminate all high frequency by straight line approximations, okay? And this is as is, I'm sorry, this is 70 millisecond as is. As is means as measured the data is. Okay, so this is for long time 70 millisecond data. And this one is a straight line approximation. So this area is pretty close compared with the previous one. But this is really down. Why? This is down because straight line approximations, okay? And as I mentioned, all the days I made the transparency of each page, just put it with a different color, put it together, you can tell clear change, but you can take just to compare two together, then you can tell how the change would be. That's what I'm explaining, okay? That's what the shock spectra is. So I want you to write the MATLAB code, good practice, and again due is like next Friday, but if you finish it, just turn in, so I'll pick it up, then I'll see. And get the shock spectra and see. Does it make sense? Think about it, why it happens. triangular pulse, bang, is the same thing. I expanded into the 70 milliseconds. But 70 milliseconds is really, really short duration. Then bang on the system. Then what would be the result? Bang! Okay, so think about it. Whoever took vibration class would help. But even if just the lecture, the last Wednesday and today would be good enough to really look at, give us some good thought when you generate the shock spectra. Okay? No questions? No questions. Alright, so now I gave you the vibration response stuff without giving you any derivation. Let me look at the next section, next end of this sections. Let me see. You have this section, right? This portion? You have it? This belongs to the beginning of vibration lecture. So without repeating the vibration lecture, I'll give you some background information, then you can get more feel. Okay? You have this, right? Hassan, you have this? You don't have this page? No? Okay. Alright, so you will get that page. I'll send it to you. Some version I don't, some version I have. Suno, you don't see this? Okay. I'll ask Higyo to send you. Okay. Just pay attention here. That's all you need. I'll get you a note. My double dot ky is minus mz double dot. You all know that. And then I can write the model diagram for this ft. This is minus mz double dot, right? So this with the initial condition y equal to y dot equal to 0 at t is equal to 0. You already saw a few times. Then using the convolution integral. Some old days it has been called as a Duhamel integral, but convolution integral is the way to get the solution. You heard about the convolution integral. Don't say no. You know. Convolution solution can be. How many of you are going to take the OSE540-101203? Take a look at it. Then that's spring quarter. I'm teaching that. There at the beginning we go all this derivations in a complete sense. Anyway, the response y is equal to integration from 0 to time t. F is a forcing function, and the small h is called the unit impulse response function. What does it mean, unit impulse response function? The physics first before the math. Unit impulse. You have a system there, bang! Then what happened? That's what the small h is. So in the small h is really oscillations, okay? So that's what the unit impulse response function is. and tau is integration parameters. And in STX, Sungwon and Yongwon out there, I see you, and you will get a copy of this convolution integral page, so don't much worry. Excitation force multiplied by unit impulse response with a time delay tau, then tau is integration parameter from 0 to time t. Okay, so this is what the solution, that's what the solution, closed form solution for that second order differential equations. And as we look at inside, f happened to be minus mz double dot, and h, impulse response function, is purely sine function. Bang! The system gonna just simply, if there is no damping, it's gonna be simply, as I mentioned the other day, sine cosine or harmonic function. All is gonna vibrate. How long? Forever, in this case, because no damping in the system. But in the reality, you have a damping in the system. What does it mean, damping in the system? Energy dissipate. Where? In the build-up structure, where the energy dissipate, such a building, joint. Joint is the location, usual location that energy, whole system energy dissipate. Not the material itself. Material damping is very, very small compared to such a joint damping. The location of the system where the energy really dissipate. Okay? So it's nice to know. In terms of the zeta, which is so-called the zeta is a couple different names. Is damping coefficient or critical damping ratio, all different name, which is C over CR, but no damping in the system here because this is undamped single DOF system for shock spectra. So sine function, right? Divided by m omega n. So this is H. So all this is belong to beginning of vibration. And the next semester I'm teaching that OSC 541. I think all of you took last spring, right? Yeah. Chorong you took? Zhongwan? No. So you will take that. Who knows? Maybe Gusto may take it. But anyway, so that's what that is. Then if you put it together, all this into the convolution integral form, you have that's the solution form. So this is integration. If you take y dot, then you have to take a derivative with respect to time t, right? Time t, nothing changes here. Time t, right? So if you take a derivative with respect to time t, then omega n has to be out, isn't it? Hmm? Then sine changes to cosine. But whether it's a sine or cosine, there's a harmonic function, right? Only phase is 90 degree different. When you put the max in front, doesn't matter whether it's a sine cosine, to get the spectral value. You see that? So that's the reason. Then if I take the time derivative, it's gonna be just, you don't have to write, I'll send it to you. If you wanna put something on your note, of course, it's no problem. So it cancels up. So y dot happened. This is spectral value. Y displacement spectra, function of omega n, if I put the max in front for all over the t range, right? Then I'm going to put this guy, no, y, not y dot, y in just the previous page, it's going to be like this. If I say this guy is x, capital X, which is a function of omega n, because it's a max in all over the time t range, so I can rewrite this as capital X over omega n. Is it clear? Very clear. No magics in there. Then sy dot, relative velocity spectra, is maximum, is a definition, right? Maximum absolute y dot. I should really put the 2 bars to say max absolute, right? Sign doesn't matter. All over the t. Then max, then I have to put them, put it here, dot. So this is x, this guy is sine, but now here's a cosine. So I said this is x, is it okay? Is it okay? Sine, cosine, all harmonic function, 90-degree phase difference, who cares, right? So this is capital X, then I can claim that sy dot is equal to this guy is equal to omega n times sy is right here. That's why Wednesday morning I wrote without this, but this is simple derivation. So now if I say sy double dot is equal to omega n times sy dot. Make sense? Equal to omega n square sy. When you differentiate with respect to time t, then change from displacement to velocity, velocity to accelerations, okay? That's what's happening there. So that's what it shows here. You will get the copy of this page by the email. Any questions?